afternoon, everyone. Thank you so much for joining us today. My name is Emily Silva, and I'm the NECAN coordinator. I'd like to welcome you to the third webinar in the NECAN Student and Early Career Scientist series, in which we are highlighting the work of students, PhD candidates, and early career scientists who are working on ocean and coastal acidification. The full schedule, along with past webinar recordings, can be found on the NECAN website, listed here, necan.org/student-webinars. And don't forget to sign up for our newsletter so you don't miss any announcements on future webinars. Throughout the presentation, if you have any questions, you can submit them through the questions tab on your GoToWebinar control panel, and we'll go through each of those during the Q&A session following the presentation. Today, we'll be hearing from Dr. Melissa Melendez from the University of Hawaii on understanding net ecosystem metabolism and carbonate chemistry at near coral reef ecosystems using moored autonomous PCO2 systems. Melissa is a postdoctoral researcher at the School of Ocean and Earth Science Technology at the University of Hawaii at Manoa. She's currently working with Dr. Christopher Sabine on new technologies to measure net ecosystem metabolism. Melissa received her PhD in oceanography from the University of New Hampshire in September 2020 under Dr. Joe Salisbury's direction. She's won the prestigious Ford Foundation Dissertation Fellowship Award, has published and presented her work locally and internationally, participated in scientific expeditions around the US East Coast, contributed to the 4th annual National Climate Assessment, and advised and mentored students from her native Puerto Rico. Melissa is also part of the Global Ocean Acidification Observing Network and the Ocean Foundation's International Ocean Acidification Initiative in the Pacific and the Caribbean. Her research focuses on understanding ocean acidification and net ecosystem response using new modeling techniques and technology. So with that, I'll hand things over to Melissa and she can take you through her presentation.
Thank you, Emily. Thank you for that introduction, and good morning and good afternoon to everyone that is connecting from the Pacific, from the Northeast or the Caribbean. It's 10 a.m. in Hawaii. So as Emily mentioned, I'm going to present today part of my work, the work that I did at the University of New Hampshire as part of my PhD. And I'm gonna also talk a little bit or just mention what I've been doing here at the University of Hawaii. And in that picture, you can see the MAP CO2 buoy that I worked. Here is the buoy. This is a coral reef system in Puerto Rico. The name is Cayo Enrique. And this is the buoy that is located like close to the reef. I'm gonna turn on my laser pointer. Perfect. So you maybe are familiar with this figure. It's showing the atmospheric CO2 concentration in from 1959 to 2020. It is recorded here in Hawaii at the Manoa station, and is the longest record of direct measurements of CO2 in the atmosphere. Today, the concentration is around 416 parts per million. And all that CO2 can be absorbed by the ocean, and around 25 to 30% have been uptake by the ocean. So the concentration of CO2 in the seawater have increased over time. And that have caused some changes in the water chemistry. And the ocean actually can absorb CO2 and react. So it produces carbonic acid, bicarbonate, and carbonate, and then decrease the concentration of carbonate. And this is what we know as ocean acidification, is the effect of CO2 in the ocean chemistry, which is cause a decrease in the pH. And not all of this species of carbonate parameters, species in the carbonate system can be measured, but we can use a combination of different ones and measure actually in the lab using dissociation constants, and we have a pretty good understanding of the carbonate chemistry. One of the parameters that we use as a proxy for calcification and the effects of ocean acidification is the carbonate saturation state, which is a measure of the carbonate ion concentration. And this is very important because ocean acidification decreased the concentration of carbonate ion, and this is used to build skeletons like coral reef systems, corals, the different mollusks, lobsters, oysters, different phytoplankton communities use this carbonate ion to build the skeletons. So some of these organisms are especially sensitive to ocean acidification. And these changes have been measured in different areas in the open ocean. For example, this is a illustration of where the longest records of carbonate chemistry have been taken. One is in Hawaii ocean time series here in Hawaii. The other one longer record is in Bermuda, the Bermuda Atlantic time series, and the European station time series ocean of the Canary Islands. These are the measurements here, and all of them have recorded an increase of CO2 in the water and a decrease in pH. Except that Bates found that two coastal stations, the one in Cariaco Station, which is in Venezuela, and the Ermingency, which is close to the Greenland in North Atlantic, have shown that the changes are being faster there, and he attributed these changes or these differences because of the effects of biological activity and physical factors are significant there compared to the open ocean stations. So there is a need for emerging technologies and methods that we use in the open ocean, but maybe adapted for coastal areas to know what are the trends of ocean acidification in coastal systems, which we still don't understand very well. In here is a figure showing the changes in carbonate saturation state with respect to aragonite. Aragonite is a form of calcium carbonate that most of the coral use to build skeletons. So that's what I'm going to refer through the whole presentation is to carbonate saturation state, aragonite carbonate saturation state. This is the changes. The big changes are in red, and the minimum changes are in blue. And we can see that from 1963 to 2003, one of the big changes have occurred here in the Caribbean. And it's estimated that the rates of saturation state are faster than most of other coral reef areas. And you can see here that also Pacific have shown big changes. Here in the Northeast is a little bit different. But it's challenging. It's challenging to measure ocean acidification in coastal areas because there is a lot of processes, and disentangle all of these processes from the signal that we measured is difficult. And so if we focus here in the coral reef systems, which are one of the most productive ecosystem in the world, we see that the changes in CO2, which I'm going to talk a little bit more about the buoy capabilities later, but we know that the CO2 changes can be due to temperature and salinity, and that's what we call like solubility effects. It can be also due to the air-sea exchange and horizontal and vertical mixing. That's why we refer to physical parameters, and also biological activity, and that includes the organic carbon cycle and the inorganic carbon cycle. in the organic carbon cycle includes respiration and photosynthesis, and the inorganic carbon includes calcification and dissolution. And this is just a schematic diagram showing the Reef biogeochemical processes, how this affects the carbonate chemistry. The strong effects are in red and orange, and the minor effects are in blue. And what I want to show here is that the organic carbon cycle, it is referred as net ecosystem production, as the integration of photosynthesis and respiration. And the inorganic carbon cycles, which is referred as net ecosystem calcification, includes the calcification minus the dissolution, can have like the effects can be in the same direction as ocean acidification, and sometimes like the effects of these processes on the carbonate chemistry can actually be in the same magnitude as ocean acidification. And with that said, this is one of the challenges of like actually measuring and understanding the effects of biogeochemical processes in coastal areas. So multiple processes affect the PCO2 and the Carbonyl saturation state and other carbonate parameters. Now, how can we measure this net ecosystem biogeochemical processes? There's different methods, and all of them differ in different spatial and time scales that they can actually measure. We have enclosure, we have the anomaly technique using residence times, we have gradient flux, and yeah, all of them differ. And it also is challenging because it actually is another economic thing that you need to actually include in your, not everyone have the capabilities of putting this type of systems. So we need to improve the methods to obtain seasonal and annual rates of net ecosystem production and net ecosystem classification in the field. And sometimes like models can help us understand a little bit more. We can apply models that are being used in open ocean, modify them to see how well they can characterize these biogeochemical processes. And then we see which type of methods is better for our area. So today I'm going to talk a little bit about the single well mixed box model that I used. So my research questions for my PhD were trying to understand what are the mechanisms that cause seasonal variability in carbonate chemistry in nearshore reef ecosystems, which biogeochemical and physical processes are dominant at seasonal timescales, and how are the biological and physical processes affecting the ocean acidification signal. And for that, there is different data sets in US that are an effort from the NOAA Ocean Acidification Program, Pacific Marine Environmental Laboratories, the IOS associations, and this buoys, I think that is around 22 right now, can measure different parameters at high frequency. I chose the only two available for the Caribbean, which is one of them is located in Florida Keys, in the Upper Keys. The name is Cheeca Rocks Reef. And then the other one is located in southwest of Puerto Rico in a coral reef system that I mentioned before, Cayo Enrique. The name of the town is La Parguera, so we refer to this buoy to La Parguera, map CO2 buoy. And these buoys can measure continuously every 3 hours surface measurements of CO2 in the air, CO2 in the water, temperature and salinity, pH, oxygen, and it have sometimes chlorophyll and other optical parameters or biological observations. One of the challenges of understanding the carbonate chemistry is that we need a second parameter to characterize the whole carbonate chemistry. And for that, I'm going to choose the total alkalinity and PCO2 pair. Some of them are better than others, and that depends on your questions. But with this one, we have that we can understand the dissolving organic carbon, the total alkalinity, and the carbonate saturation state within like the uncertainties acceptable for the global ocean acidification network. To understand biogeochemical processes, it would be better if we maybe measured total alkalinity and pH, but there is some limitations because the instrumentation that is available, actually there is no instrumentation available that can measure total alkalinity in the field at high frequency. And for that, we model total alkalinity based on temperature and salinity changes. We took and analyzed the data from different cruises around the Caribbean and Atlantic, and we observed that our TA based on salinity is not that good. It's like maybe salinity is not the best predictor of total alkalinity, but it's not that bad. And this decreases here in total alkalinity and deviation from this linear relationship is just due because of that biogeochemical processes. In this case, is some calcification is happening here. But when we summarize the data and create this climatological or seasonal cycles, our model is shown on the shown here in the black line, and the blue are the measurements that we take and analyze in the lab. And you can see that the model is close or within the uncertainties or natural variability of the sites. This is for Cheeca Rocks, the upper, and this is for La Parguera. So now that we have our two parameters, we have direct observations and time series data. Cheeca Rocks have 9 years of data, and La Parguera I use 11 years. So the data goes from 2009 to 2017, and that doesn't include the hurricanes in 2017. So we have different time series: salinity, seawater PCO2, air PCO2. With that, we can also calculate the seawater air PCO2 gradient and the CO2 flux. When the CO2 concentration in the ocean is greater than in the atmosphere, then we have that the system is a CO2 source. And then when the concentration of the CO2 in the water is less than in the atmosphere, then the system as a CO2 sink. And here we can see some like interannual changes. La Parguera seems to be a CO2 source through the whole year, and Cheeca Rocks seems to change between a CO2 sink here to a CO2 source in the fall. But now we have the model observations. We have dissolving organic carbon, total alkalinity, pH, and aragonite saturation state for both stations, for Cheeca Rocks and La Parguera. And what we did was that we summarized all those years and create this climatological figures and climatological to understand the climatological conditions at the sites. So here we have our model data or our direct measurements in black, and we have the discrete data, the data that we analyze in the lab in blue, and some red dots indicates another instrument that was just complementing the data during different years. And with this, I just wanna say that we have a robust quality data to understand the carbonate chemistry and to understand biogeochemical processes. These methods and this data is available at the NOAA National Center for Environmental Information, NCEI, and I also published this in the Journal of Geophysical Research. So if you want to know a little bit more about how we calculate this and the methods, I recommend that you look for that paper where everything is explained in a little bit more detail. Let's go to the results. I'm going to just pick 2 different parameters and tell you a little bit more about the climatological conditions at both sites. Cheeca Rocks is in red and La Parguera is in black, and this is the carbonate saturation state. And we observed that the Cheeca Rocks experience greater seasonal amplitudes than La Parguera, and that Cheeca Rocks is actually around 40% higher during the springtime than the fall. And remember that the aragonite saturation state is a proxy for calcification. So higher numbers are easier to calcify, lower numbers are more difficult to calcify, or more energetic demanding for those organisms. And just to have an idea, some colleagues have found that it doesn't have to be very low to show that there is some dissolution of the calcium carbonate minerals. Yamamoto in 2011 found that values that are less than 3.7, at those values you can observe some dissolution of the highly soluble calcium carbonate minerals like high magnesium calcites, and those minerals are found in like the cements that build or that stick together the reef, kind of. So values that are less than that can actually increase the possibility of dissolution of different calcium carbonate minerals. And this is the CO2 flux. This is, as you remember, values that are positive indicate that the system is a source, and values that are negative indicate that the system is a CO2 sink. And we have that for Cheeca Rocks, there is a transition from the spring to fall, from sink to a source. And La Parguera seems to be a source of CO2 through the whole year, even though the winter time and kind of like beginning of the spring is like low values. So to what is causing this seasonal changes and which processes are driving these transitions, and why La Parguera is always a source of CO2 versus Cheeca Rocks. To understand this, we need to understand where the water is come from and what are the benthic communities that are in these sites. So for that, we analyze data that were collected using ADCPs or current measurements. And ADCP is an instrument that measured the speed of the current and the direction, and it was located at the buoy site in Cheeca Rocks for a year. So that data shows that the current is around 7 kilometers per day, and the water is coming from the north towards the southwest. No seasonal variations, and we can see here this is a polar histogram of the current speed. Blue are current speeds that are from 0 to 5 centimeters per second. And the water, we can see here that green is seagrasses, the orange are benthic communities that are scattered corals and sediments, and the red ones are just like patchy corals, and the big coral site is here. The buoy is located just right there. So the water, the Cheeca Rocks represent water that is about to contact the reef. So all this water have been coming from this area, and it's gonna like pass to the buoy and then contact the reef. So the benthic communities that are affecting our measurements are probably from seagrasses and calcium carbonate minerals or sediments. At La Parguera, we have here, this is the Cayo Enrique, and Cayo Enrique has some mangroves, have some, the crest that have some coral robles, have sand and seagrasses, and the forereef. So the buoy is located here in the southwest of the reef, in the forereef area. And again, the ADCPs were located here in 2 locations, and they were taking measurements for a year. And the results shows that the current is around 1 to 1.5 kilometers per day towards the west-northwest, and it's in good alignment, like follows this morphology, this forereef morphology. So it stayed there for longer time than at Cheeca Rocks, and the water represents, the measurements represent the water that has been exposed to the reef for 4 to 16 hours. That's a little bit more than at Cheeca Rocks, which is a couple of like 1 or 2 hours. And the benthic communities are different than Cheeca Rocks. Here, the benthic communities affecting our measurements are corals. Most of those corals is only 10% coral covered, but most of those corals are just soft corals, and a lot of coral rubble. So our measurements are indicating the net ecosystem classification. All this processes from these communities in Cheeca Rocks, communities that are more like seagrasses and calcium carbonate sediments. So which biogeochemical processes may prove dominant? For that, we use a property to property plot in this graphical approach. So the net effects on these processes can be evaluated using this graphical approach of TA and DIC, where the reaction path can take on variable slopes depending on the ratio of organic to inorganic carbon production and consumption. So based on this, we can understand how the water is being modified since travel from like the offshore and member. So if our data lies here in this quadrant, then we understand that this is calcification depending on the slope of the data. So here are the results. This is data that is from the bottle measurements that we take every 2 weeks and analyze in the lab. These are not the buoy measurements. And this data indicates that Cheeca Rocks, there is some calcification at Cheeca Rocks, mostly in summertime. There is also some dissolution and respiration in the fall. It seems that there is not much of the production or not a lot of respiration, but it seems that the calcification and dissolution signal is the dominant one. This is how the coastal ecosystem modified the offshore waters. At La Parguera, we see that there is a strong calcification signal and there is some dissolution too. Not as much as production and net ecosystem respiration. So yeah, significant contributions from calcification dissolution, and here some respiration at La Parguera. Yep, we went through all that. So that was the discrete data. And now let's see the buoy data. And for that, we used apparent oxygen utilization using the oxygen measurements that can indicate some of the biological and physical processes. And we also normalized the PCO2 data, normalized by the temperature, and that removed the temperature effects. So here what we see is like the biological effects on oxygen and PCO2. And we have that if there is negative numbers, indicates that there is photosynthesis. If we have positive numbers of A or U, we have that there is respiration. And we also, this is the mean conditions, mean atmospheric CO2, and we have positive values that indicates that the system is a source, and negative values that indicates that the system is a sink. This is the data from Cheeca Rocks, and we can see that there is some hysteresis, and this is like an elliptical shape of the data. And we can see that the systems change from source to a sink from winter to spring. And then there is another transition from photosynthesis or for autotrophic conditions to heterotrophic conditions from the spring to summer. And again, another transition from summer to fall. The data looks different at La Parguera. La Parguera, the biological processes seems to be muted, or the effects of these biological processes on the carbonate chemistry seems to be muted. But there, if we zoom in, there's also some like hysteresis and a transition between autotrophic to heterotrophic conditions. But the data seems to, like all the time, again, like La Parguera seems to be a source of CO2 with no seasonal variation or transition. And we attribute this shape of the data and this hysteresis due to the effects that the benthic communities have on the water chemistry. For example, it seems that the benthic communities in Cheeca Rocks have a stronger effect in the carbonate chemistry compared to La Parguera. This is also related to other processes that can affect the carbonate chemistry or the biogeochemical processes. So we have, in summary, we have two different approaches to understand which biogeochemical processes is dominant. We use the autonomous measurements and we use the discrete measurements. And the autonomous measurements includes the PCO2 and the oxygen, and the discrete measurements include the total alkalinity and dissolved inorganic carbon. And we see that this data actually is showing different things. There is some production or some like photosynthesis, but the discrete data didn't show that there was some photosynthesis. So why is this showing different things? We think that the data represent different spatial and time scales. For example, the discrete measurements have been like integrated over longer time scales and over longer spatial scales. These measurements represents biogeochemical process that have been around the Reef platform for days. And the autonomous buoys or the measurements at the buoy is more like high frequency data of the benthic communities that are around the buoy. And also there is some difference of what we are measuring. So the different carbon pools, it seems that there is a huge difference when we compare, when we use different parameters to understand biogeochemical processes. For example, we are looking at PCO2 and probably pH that are more fast response parameters compared to DIC and total alkalinity that are more like slow response. So these carbon pools can indicate different biogeochemical processes. So it highlights the need for more comprehensive observing systems that includes both the fast response and the slow response carbon pools. So that was interesting find. So now that's our observational approach. Now we're moving to a modeling approach. What I did was that I applied a model well-mixed single box model, a mass balance approach that been used before in open ocean systems or time series. And here we have a schematic diagram of the buoy where we did that. We wanna we apply different equations and different approaches to understand the air-sea exchange, to understand the processes that affect the solubility, the PCO2, and then some of the other approaches to understand the biological processes on PCO2 from the benthic communities and the column. And again, this was submitted and is under review in Limnology and Oceanography journal. So hopefully we get some response soon from the journal. So these are the results from the mass balance model. And here we can see the different processes that affect the PCO2 signal. We have the observed changes the observed changes in PCO2 in red, the solubility effects on PCO2 in blue, the horizontal mixing and the air-sea exchange in green and purple, and the biological processes are in black. This is for Cheeca Rocks, and the lower panel is La Parguera. And what we see here is that horizontal mixing and air-sea exchange had no significant seasonal changes and is almost neglected at the sites. But we see that Cheeca Rocks, the biological processes are greater than the temperature effects, while at La Parguera, the temperature effects are greater than biological signal. And if we take a closer look, this is a little bit more to understand how these biological processes affect the PCO2. We have that at Cheeca Rocks, it can actually increase the PCO2 by 138 microatmospheres, while La Parguera, the biological processes can only increase PCO2 by about like 11 microatmospheres. So most of the changes in PCO2 are due to temperature. In here, in Cheeca Rocks, most of the changes are due to biological activity. And this is due to different latitudinal differences in temperature, and also, again, because of the biological composition between the sites. So the model have the capability of understand or to like estimate how fast are these biogeochemical processes changing. So here we have the rates of net ecosystem production and net ecosystem classification here in the lower panel. The upper panel, we have that these are millimoles of carbon per meter square per day. And we have La Parguera in black and Cheeca Rocks in red. Positive values indicate photosynthesis and negative values indicate respiration. We have here how this seasonal variability in biogeochemical production, net ecosystem production. In here, in the lower panel, we have net ecosystem classification in millimoles of calcium carbonate per meter square per day. We have positive values that are calcification and negative values indicate dissolution. And we can see that there is very low rates of calcification from January to April. We have that both sites are net heterotrophic and net erosional on annual basis. That means that most of the time there is just net respiration and net dissolution. The dissolution persists for more than 50% of the time. And that dissolution and heterotrophic events dominate during late summer to fall. And we can see here how the rates are higher for La Parguera of dissolution in summertime, but then in the winter time, it seems that the rates of dissolution are higher at Cheeca Rocks compared to relative to La Parguera. And this is interesting and concerning, just related to the, this is the beginning of the shellfish spawning period. This is how this data can be useful for coastal managers. For example, this is where the shellfish like lobsters and corals release their larvae. And that increased the sensitivity of calcium carbonate dissolution during this time is the more sensitive one. This data is very rare and very unique because we still don't understand very well or have the capability to actually measure in high frequency in situ conditions the net ecosystem classification and net ecosystem processes. So this is one of the first times that we have this type of measurements. So where do the results lie? For example, here I just put my data and compare with other areas in the Caribbean, including like Bermuda, Belize, Barbados, and these are the gray dots. Our data, La Parguera, shows that for 10% coral, and here, yeah, let's explain this. The x-axis indicate the percent coral covered, and then the y-axis indicate rates of calcium carbonate in kilograms of calcium carbonate per meter square per year. And we have two different methods: the chemistry measurements, which is what we did with the model, and then the census methods, which is more specific and takes into account bioerosion and is more specific to the organisms. Still, our results agree with the other results and taken in the same area, and it shows that 1/3 of the Caribbean reefs are already net erosional, and it seems that the threshold is around 10% coral covered. Like around 10% of coral covered, the system seems to show like net erosional conditions. And yes. So now that we have that data, we can ask other questions, like for example, when net ecosystem classification is 0, can we actually get some geochemical thresholds that can tell me like, okay, at this point, the net ecosystem classification is going to be 0. And this is data from La Parguera showing the different seasonal variability, is showing a hysteresis as well. We have in the x-axis the carbonate saturation state, and the y-axis indicates the rates of net ecosystem classification in millimoles per meter square per day. And here this line indicates the saturation state, the mean saturation state for the ocean. So La Parguera seems to like be below, or these values are below the ocean mean. So these biogeochemical processes are decreasing the carbonate saturation state below the mean of the ocean. And there seems to be 2 transitions where the net ecosystem classification is 0, one in the fall and one in the spring. And yeah, there is a hysteresis pattern, which complicates our ability to actually evaluate those geochemical thresholds. For example, in the lab and other methods have shown that there is a linear relationship between net calcification and carbonate saturation state, but that's not our case. So this data is only taken in the lab and taken in a short time scales, while our data includes high frequency measurements for longer time scales and indicates more an ecosystem variability. So net ecosystem classification and net ecosystem production is 0 at omega 3.75 in April and 3.5 in December. At Cheeca Rocks, we have the same exercise, and we have that there's more like a linear relationship between net ecosystem calcification and calcium carbonate saturation state. Still, it's only 30% of the variant that is explained by omega. So it's indicated that maybe omega is not a good predictor of the long-term changes in net ecosystem calcification. So simple linear trends cannot explain the feedback between these processes and the reef water chemistry. And we have the net ecosystem classification is 0 when omega is around 4. And that is actually very close to the mean ocean value. So it seems here that this biogeochemical processes decrease omega during the fall and part of the summertime and winter time. And then spring biogeochemical processes increase omega, and there is like a summer transition to more calcification and more production. So to understand how net ecosystem classification and net ecosystem production affect omega, we use the property to property plot of DIC and TA, which shows the different net reaction paths or slopes that can yield to different changes in net ecosystem calcification and net ecosystem production ratio of the seawater saturation state. So we have here that the carbonate saturation state can change. It's in this color band. We have the lower carbonate saturation state is in red, and then higher saturation states are in blue. And we have that depending on the ratio of these biogeochemical processes are the effects of omega. And it seems that for our data or our total alkalinity and DIC range in the systems, the ratio is, our critical ratio is 0.87. And that means that at this ratio, there is no change in calcium carbonate saturation state. Higher ratios decrease the saturation state, lower ratios increase the saturation state, and higher ratios decrease the saturation state. And this is showing the data. Net ecosystem classification in the y-axis and net ecosystem production in the x-axis, and our critical ratio is here in the red line. So we have that at Cheeca Rocks, the data actually align very well with the critical ratio. So seems that the biogeochemical processes don't have a lot of effect in or doesn't change much the carbonate saturation state. But at La Parguera, the ratio of the biochemical processes can actually decrease the carbonate saturation state, which means that the surface waters at La Parguera are likely to be affected by ocean acidification sooner and more strongly than at Cheeca Rocks, for example. And to understand how these ratios change over the months or over the year, we have here that indicating the NEC to NEP ratio. And this is our critical ratio. We have that in the winter time for Cheeca Rocks, which is in black, and La Parguera is in red. We have that in winter time, there is an increase of omega, probably due to an increase in photosynthesis, and then a decrease in omega due to an increase of respiration and calcification during the summertime and fall. At La Parguera, most of these ratios are above the critical ratio, so it means that there is a decrease in omega through most of the year. So in summary and conclusions, both sites are net heterotrophic and net erosional on annual basis. Respiration, and particularly in late summer and fall, appears to be an additional source of CO2 to the systems and can make calcification more energetically demanding. And the Caribbean reef are exhibiting long periods of net dissolution. We have here the numbers and how fast these biogeochemical processes are changing. For example, net dissolution is at a rate of 0.7 at 0.68 at La Parguera and 0.4 at Cheeca Rocks kilograms of calcium carbonate per year. So this actually is in the lower end of a typical calcification ranges for other reefs. These methods can be applied to other sites and can be used in combination with other approaches. There is, remember, like around 22 map CO2s around the US. Autonomous capabilities can be used to detect metabolic processes sensitive to ocean acidification, but it needs some other parameters, like, for example, oxygen, and a good understanding of where the water is come from. And future research efforts should be directed at improving our understanding of the drivers of both calcification and organic production on a long-term scales. So future work we have now that we can look at the interannual changes in net ecosystem classification and net ecosystem production. For example, here we have interannual changes in net ecosystem classification for Cheeca Rocks and La Parguera. And we found that higher dissolution rates were observed during, like, for example, bleaching events here in 2010 at La Parguera. My postdoc research, I work with developing instrumentation to measure total alkalinity and pH, and this can improve our model and understanding of the diurnal drivers of net calcification variability in the field. We are working with a sensor that can take measurements of total alkalinity and pH at high frequency, and we hope to apply this model and also take measurements in situ and compare them. So we can scale up to other areas, and now we can compare different ocean settings, for example, now that the Pacific versus the Atlantic reefs. And here is just a picture of how our sensor deployments look like. There's 2 buoys in Hawaii, in Kaneohe Bay. And so we work mostly at the buoy that is close to the reef. And we put some instrumentation close to the coral reef area that we are trying different settings and just trying the new sensor. And we found there's already data that we can see how the pH and total alkalinity change over time. And these are the diurnal changes. We can observe some calcification during the day and some dissolution during the night, and some photosynthesis during the day and respiration during the night too. So we hope to understand a little bit better how these biogeochemical processes affect the carbonate chemistry in Hawaiian coastal areas. And with that, I want to say thank you to everyone, my community members, my co-authors, and the funding that part of that is from the Ocean Acidification Program, the IUS Caribbean Association, and the Northeast Caribbean Association, Northeast Association, the US Marine School and the Earth Science Grad School, the Ford Foundation for the Dissertation Fellowship, and everyone that helped. And with that, I can take some questions.
Thanks, Melissa. That was great. There are no questions right now, so I just wanted to remind everybody to submit a question if you have one, or a comment through the questions tab on your control panel, right on the side there, if you have any. That was a great presentation, Melissa.
Thanks.
We have a couple minutes left, so I'll just give it a minute, just in case people are typing. I don't want to rush anyone. So we do have one question come in so far. They're asking if you could talk a bit more about how you're measuring total alkalinity autonomously.
Oh yeah. So it's a CFET sensor, as maybe you're familiar, but there is CFET is a solid state sensor, and it can measure pH and then simultaneously actually measure total alkalinity by titration. This is kind of new, and is Ellen Briggs is the one that developed this technique at the Scripps Institution. There is another sensor that is being developed by the Pacific Marine Environmental Laboratories, and right now everything is a prototype, and we are different methods, but both of them are being compared next to each other.
All right, cool. That's still just the only question. Oh, just got another one. What are the bottom line restoration and management recommendations?
Good question. I encourage people to work with other stressors, trying to minimize some stressors, for example, sedimentation, overfishing over these reefs, and try to minimize, the additional pressures to the systems. There's coral reef farms that have been happening, and you can restore kind of like the reef slowly. There is other measurements or other applications with carbon sequestration, and how can we actually remove CO2 from the water. And for that, there's been studies that shows that seagrasses are good for that, and kelps farms can actually remove the CO2. So it seems like Cheeca Rocks is doing a little bit better than La Parguera because it have the influence of seagrasses that are upstream of the buoy, and the water is a little bit more like, it doesn't stay there for a long time, so it's like a more flushed area. And yeah, some of this is a little bit tricky, but those are my recommendations. Try to work with the coastal managers to reduce the stress on these systems, as sedimentation or fishing or pollution, plastics, that kind of things.
Mm-hmm.
Yeah.
Do you have any thoughts on what sets the omega threshold for net dissolution in your reef systems and in reef systems in general?
Difficult to tell right now. It seems to change reef by reef, so it's not like one value for all reef systems. It seems that it's very specific for every ecosystem. It also seems that it's not really like a linear relationship. It seems a little bit more complicated than that, and we are looking to see other thresholds, like for example light, turbidity, net ecosystem production. In some of that is like when is calcification zero, is when net ecosystem production is the zero as well, or close to zero. So it seems that calcification and dissolution are more related in the systems to the organic carbon cycle than to omega. But it could also be because there are other factors influencing omega. So it seems that systems that have this hysteresis, it seems that the relationship between calcification and net ecosystem production is tight, tighter than, for example, at Cheeca Rocks, where there is not as much as a seasonal hysteresis between net ecosystem classification and omega, but it's because net ecosystem classification is not that related to production, if that makes sense. But there we need to understand the drivers of both production and calcification.
Okay, so it's 4 o'clock right now. I just want to be respectful of everybody's time, but we have 2 more questions. And I just want to remind everybody that this is being recorded. So I'm going to ask Melissa these last 2 questions, and then if you can't stay for the answer, the recording of the webinar will be up on the website early next week. So come back and check that out. Okay, so the second to last question is, will you be integrating benthic monitoring data, coral health metrics, or nearby co-located water quality data with the data coming off of your newly deployed sensors in Hawaii? And that's the end of the question. There you
go. Yes, there is some data. I'm not going to be exactly working with the biological measurements, but there is, for example, corals and that grows under the buoy, and there's been like someone else that is looking at that data. There is some other structures from the National Coral Reef Monitoring Program that are at the reef site. And also with the benthic measurements that we put, there's also, we are taking measurements of oxygen and pH from a CFET, that's another instrument. And then the new instrument that takes pH and total alkalinity, and then another instrument that is being tested by the Pacific Marine Environmental Laboratories, which is taking measurements of total alkalinity. And we also looked at the data from the buoy. And yeah, we have like a suite of instrumentation and data, and we are going to look at all that all together in a more holistic way, if that makes sense, to try to estimate net ecosystem classification and production in different ways, using different approaches, using different methods. My focus is to, we are going to deploy drifters. So my focus is to use this new instrumentation, put it in drifters, and calculate net ecosystem classification and production from the offshore to the inshore using Lagrangian methods. So different ways, a collaboration between different people and different projects at the same time, but my focus is with the drifters.
Okay, and the last one, have any invasive species impacted calcification in the reefs?
Good question. I don't know exactly. I could think about maybe some invasive algae could have some effects if overgrows where close to the buoys where our measurements are taken. It could be, but I don't have data. It could be if you have data of a time series of percent cover of that invasions of that algae, then you can look at the chemistry and see like if that correlates with an increase of algae with that increase of dissolution or respiration. And that's how this chemistry time series are very helpful. In this net ecosystem classification time series can also indicate some health or different biological processes that are related to the chemistry. But yeah, we will have to like look at the data. I don't know for these sites. I didn't find anything. related to that. But it could be the case of another station, for example.
Great, thank you, Melissa. So that was the last question. So that'll conclude our webinar for today. The recording, as I said earlier, will be available on the NECAN website early next week. The next scheduled webinar is on Monday, March 8th at 1 p.m. The registration link, along with the title and abstract for this presentation, will be shared through the NECAN mailing list, as well as on our website. I've also been posting on the Ocean Acidification Information Exchange, and I highly encourage everybody to go request an account there if you haven't already. I've included the link here. It's oainfoexchange.org. And it's a great place to get more information about OA, to stay informed on webinars and events, and engage in conversation. I've also included my email down there as well. If you had any more questions for Melissa, you can email me and I can reach out to her, or any other questions about our webinar series or NECAN in general. So thank you, Melissa, and thank you everybody else for joining us today.